welcome to the session. Greeting of the day. In today's class, we are going to talk about the various welding heat affected zones. We know we are going to use the heat source for welding purposes. Those heat not only melting the workpieces, but also the heat is distributed throughout the workpieces. At center point, we want to weld these two specimens. There is a gap. At two members we have taken workpiece A and B, and we are going the butt welding. Groove has been taken and welded. And we are using some other heat source of gas flames or arc or resistance or solid state joining, whatever it is, we are making the weld joint. That we agree. But here you see, the heat is supplied not only absorbed by the filler wire, which is going to melt and deposit, not only absorbed by the fairing surfaces, which is have the edge preparation, but also the heat is distributed throughout the workpieces. Until it is distributed, heat is absorbed there. Right. So those zones are called as heat affected zones. The zone, which one is at center, which one where we have taken the groove that is going to melt and deposit, that we call it as a weld zone. But after the weld zone, here see I have marked this zone is called as weld metal. Weld metal. Which one? This zone. Outside, see this, we know this. So this top zone is called as a face. So here our actual welding, above content we call it as a safe face zone, and similarly we call it as a bottom zone as a root zone. And this all corners you see A, B, C and D, we are naming as a weld toe points. This is a weld toe points. It should be blended, not to be 90 degrees. See here in this 90 degrees formed, it is not good. The sharp corners will initiate the stress points. So it should be welded to be smoothly blended here. Smoothly blended here, that is other points. We came. Now the weld zones we are in talk. So here the boundary where it is the fairing surfaces, the dotted line shows the actual workpieces of edge preparation. When it is heated, this dotted lines also, it means the fairing surfaces are heated and melted and converted the boundary zones here. You see, this is the boundary zones. So it will become like this. The boundary zones it will become. The welding occurred there. But the heat is absorbed, melted. But other zones, the majority of heat are absorbed for welding. The remaining part of heat are distributed in the workpieces. Where it will go? It should be absorbed and distributed. It is distributed. With respect to distributions, we are giving names for that. That is called as a heat affected zones. That zones we are going to see. See, now here the design throat thickness, the total thickness of the specimen, maybe 10 mm, 20 mm, whatever it is. And how far we are welding, actual thickness, what we are welding, the actual thickness is the addition of this reinforcement along with the addition of this root. Both combinedly we call this as actual throat thickness. This is a design throat, that is a thickness of the specimen. But during welding, the cap is formed, the reinforcement, and the root also full penetration we are doing. That is why the total together is called as a actual throat thickness. Where is the excess here? You see, above this is excess. Excess cap height or otherwise called as reinforcement. So this is the idea of the weld zones. Now we are coming to the heat affected zone. I am comparing this heat affected zones with respect to our iron carbide phase diagram. For steel, we know the melting point is around 1550, and when it is coming down, here it is a liquid zone, here it is a liquid zone, and when it is coming down from the liquid, it is converted into austenite. It means it is started to solidify. And then after austenite, we have the ferrite here. We have the ferrite zone, and then to the room temperature it comes down. I am comparing the steel, this phase diagram with our heat affected zone here. I have taken this part, one half of the part I have taken equally. When the heat is distributed in this side, it should be distributed in that side also. So we consider we are taking the heat distributions in such a way. One half I have taken. At center, this is the part A and part B were welded. High heat is observed at the center point. We know this because we are doing welding in this location. This here the edge preparation is done. Therefore, this point belongs to this melting point. You see, this center point, this zone belongs to zone 1. Zone 1 we call it as a solidified weld metal. It is going to solidified weld metal. Then later, next to that, a small boundary is there, the transaction from the liquid to the solid. So it is when this comes down, the temperature reduces, it is going to be. Next zone nearer to that, I am calling this as a unmixed zone or remelted fusion boundaries or zones. Fusion boundary here between the fusion boundary. From there, the other heat affected zones are forming. It is a non-melted zone. This zone belong to melted zone. And we are not talking about that. We are going to talk about the heat affected zones only. This is here the fine surface, edge preparations are done, filler metal deposited and welded. Welding needed we have done. But heat is distributed further towards these locations into workpieces that we are going to see. So what is there the next to that zone? The next to that here, you keep on noticing that the temperatures keep on reducing as like from the high temperature observed melting has been done here for welding 1500 and keep on heat distribution is lower from 1500 it is around 1200, this location around 1000, this location about 800 and this location around 600 400. So because heat observed, it is observed here, the temperature is decreasing from the center to the last end of the base material. See, next one, this zone, the next heat affected zone becomes the coarse grain heat affected zone. What is this coarse grain? We have seen about the solidification process that in solidification, when it is quickly cooled, it is not finding time to grain development. Therefore, it is become a finer grains. But here we have the temperatures around 1200 to 1400, this zone. I am talking about this zone around 1200 to 1400. Therefore, this zone will take more time to reach its original state. In the meanwhile, what happens? In the meanwhile, the grains will develop. From the liquid, it has to come down. In the similar way, this heat absorbed is 1200. Here the heat absorbed temperature is 1500, therefore it is melted. But in this zone, the heat absorbed is 1200, it is not melted because the steel's melting point is around 1500. This zone. But it has to come to its original position. Therefore, during this process, the coarse grain will develop. Temperature higher, it should comes down. At the meanwhile, the grains will develop. Therefore, it is called as a coarser grain. When then the finer grain will form, when there is a temperature is less, when there is a material is not disturbed, it will form the equiaxial finer grains. See, next one. And then next, what is that? Here the temperature is lesser than as compared to 1200. See here, the coarser grains are formed. But next to the zone, here I am talking about this zone. So this one. This zone, what is the temperature here? It is around 900 to 1100. It is lesser than the top. Heat absorbed here from the melting. Heat is supplied here for melting. But it is absorbed in this workpieces. So here it is absorbed 1200 temperature. Here it is absorbed around 1000. As compared to the coarser grain, the temperature is lesser. Then it is not finding time to develop the grains into coarser. Therefore, it is nucleated and then it is solidified. So that is, we are naming this as a finer grains. Right. Next, further the temperature is reduced. What is this zone? I am talking about this one, zone 5. Intercritical heat affected zone, and it is reduced here, and then last tempered heat affected zone. Now, you see, this zone, we are coming down the critical temperature. For steel, the critical temperature, we are naming this as a 723. We know this. Above that, the phase changes occurs from alpha to acetylene. Below this, there is no phase changes occur. Entirely, the ferrite zone will be there. But here, the treatment of tempering treatments are done for stress relieving or other purposes are done. Therefore, this small change in the grains are occurred. You see, from here the grains are looks very similar. It means this is zone 6 and zone 7 looks very similar, but it is lightly tempered. Then at the last zone 7, I am calling this as a unaffected zone. Heat which is developed at this center point is not reached those locations. It means it is less than that of the even 600 degrees centigrade. It is less than that of the critical temperature. Therefore, the microstructures have not changed. When we are above this critical temperature, the microstructures are changed. See, here intercritical, finer grains, coarser grains and welded. But below this, there is such huge changes are not takes place because there is not sufficient temperature, not sufficient heat are there to change the phase changes. By the iron carbon diagram, phase changes will occur above the critical temperature of 723. Therefore, these zones have not received that temperature. Therefore, it is not changes are not takes place in the microstructure level in the heat affected zones. If heat is not affected, then we are naming this as a base material. We have already taken the base material, we are supplying the heat and we are welding. So during welding process, heat is distributed towards the other locations, but it is not reached the last end point. It is reached here 1500, 1300, 1800, 723 and less than that. 723 less than that, even though the heat is 300 or 400 or 600, there is no changes occurs. Therefore, the grains as it is available, as like the microstructure of base material will be here. Therefore, I am naming this as a unaffected base metal. Unaffected base metal. So this is how I am classifying this heat affected zones of the welding process. From the huge temperature to the low temperature, heat distribution, melting, first it will become more heat absorbed, coarser, less heat absorbed, finer, and then lesser than that reaching the critical temperature, below that no changes, so it is slightly tempered, the tempering temperature of 600, 500, and less than that it is a microstructure not even changed, unaffected, that we are calling as a base material. So that is how I have given in some colors. So weld zones, here I have skipped to the iron carbon diagram. Weld zones, then solid liquid transactions, from liquid to solid, here there is no change, faint surface is only melted, other things are, this is liquid, this is going to be solid, this is going to be solid, that is called a solid liquid boundary here, this boundary, this yellow color I am naming this solid liquid boundary. Then we have the grain growth, maybe coarser grain, finer grains, partially tempered zone, unaffected zone materials are there. So in the previous diagram we have seen a large thing, but it happens only few, see, only it covers only few, other things are base material. This belongs to base metal. This belongs to entire base material. Heat is not heat is not there to reach those all changes less than 723. So that is what. So I want to represent here the heat temperatures are lighting flames. Monitoring of the heat input, how to do? Maybe 1500 it is melting point, it looks like when it is seeing it looks as a dark bright yellow color. So around that later 1200 and 900 red hot condition, this is the red hot condition, 900 zones, 600 and 300. So just for identifications I have given. For understanding how far this distributions of welding done, we are keep on moving at the other side. We have welded here and we are keep on moving there. What happened to this location? The temperature is reducing. It also crosses melting at 1500 and then it is keep on reducing one by one. Heat affected zone experience more heat for a long enough a period of time. Therefore, the layer undergoes microstructure. The layer undergoes the microstructural properties changes that differ from the parent material. These properties changes are undesirable and ultimately serve weakest part of the heat affected zone. We see this change in microstructures, this change in grains, coarser grains, finer grains. So this does not have this ductile nature, does not have such high mechanical properties. It will become brittle. These zones become brittle due to rapid heating, rapid cooling process. Therefore, it is to be minimized. Heat affected zones to be minimized. Then what we should do? Heat input should be given minimum. If heat input is given minimum, heat distribution will be minimum. Then obviously heat affected zone will be minimum. That points we should take in care. The microstructural changes are leads to, what are the effects we are getting? Residual stresses, strength, reducing the strength factors, it is reducing, increasing the brittleness, most important, micromatrix may form, rapid cooling. So decreased corrosion resistance also will be there. This all efforts to be take care, and therefore HAZ cannot be avoided, but if it comes, we can't able to avoid. Heat distribution is there, obviously it distribute towards the workpiece also, but it should be minimized. Less heat input we should give. Heat affected zone can be vary in size and strength factors. The extent and magnitude of heat occurrence is inversely proportional to the thermal diffusivity and cooling rate. So how it is dependent, heat affected zones are dependent on two factors. One is thermal diffusivity and cooling rate. How far the thermal conductivity of the base material, how far it absorbs, how far it is absorbed, how far the cooling rate is there, how far it is cools down. So depending upon these two conditions, heat affected zones also will differ. Accordingly, mechanical properties also will differ. So when the material thermal diffusivity is high, heat affected zones are small. Cooling rate is high, heat affected zones are small. Cooling rate to be high, then it become, we are not getting, heat affected zones become getting minimum. If it is reversed, see, thermal conductivity diffusivity is low, it is not going outside. Thermal conductivity is not moving outside. Cooling rate will become low, obviously. If the cooling is become low, heat will be keep on distributing to the until other end process. If it is keep on distributing to the other end, it become heat affected zone will become high. Length it will become wider, and obviously heat affected zone become high enough to make those things. Increased temperature, longer welding times results in creating the wider heat affected zone. Creating the wider heat affected zone. So, like plasma arc welding process, high current and faster welding speeds result in smaller heat affected zone. We have to keep intense heat at a specific point, and with the arc length should not be long enough to distribute. See, when we are having the weld specimen like this and we are arc length is here, what happens? It will not come directly like this. Arc is generated in this way. In this way only. Now I am reducing the arc length from this location to this location. What happens? Even though here the arc will be here formed, but how long it distributes? It will not distribute like this. It will not form, but it will form like this only. So arc length reduction, concentration increases. Therefore, you can go for deeper penetration. Wider heat will not be fall on the other zones. Other zones it will not fall. It will fall in the specific zone only. So we can able to avoid heat affected zone by using the short arc length. Long arc length is not recommended. Oxyfield welding uses the high heat input and increasing time, and so a wider heat affected zone is formed. Laser and electron beam welding gives a highly concentrated, limited amount of heat, results in a smaller heat affected zone. See, where the material thermal conductivity is high, HAZ will be small. Where the cooling rate is high, again the HAZ will be small cases will form. Near fusion boundary, a coarse grain is formed, it increases the ductility. After that, what happens? We are talking about the zones, various zones now. After that, the finer grains are formed. We have seen a weld zone is formed here. But here, this is the coarser grain because heat is absorbed more. And later we have the next zone as a finer grains. and next zone as a maybe parent metal which is having the distribution of heat is getting a reduction. Therefore, first it is forming the near to the fusion boundary, it is coarser grains are formed. After that, after these things, here, this is the coarser grains. And later after that zone, we are getting the next one of final grain zone. After that we are getting the tempered zone and similarly the base material. See how this factors original picture taken from the after welding process. See, this is the weld fusion zone. So this zone you can see a fusion zone occurs. But related to the next one, see here the heat affected zones are there for a short while. Heat is distributed here, but it is not distributed to that spot. It is a base material. Similarly here also. Here the fusion welding is there and boundaries and small light heat affected zone and the base material. Here there may be plasma arc welding. Arc length is very short. Here the intense heat is supplied and therefore it is not possible to go distribute over the base material. Therefore, it is containing the narrow heat affected zone. So some other images I would like to show you. Here the fusion welding is there. And then the heat affected zone 1, heat affected zone 1, 2, 3 and at last we have the base material. So such changes will be there. See here also, it is a base metal, we have welded there. Nearer to this non-melted but heat affected zone, see this side, it is distributing there. Here the microstructure you can see it is columnar, lengthy, it is more heat, not equiaxial grains. But here nearby to that, here are equiaxial. Here are equiaxial grains are there because it is finer, non-affected. Similarly, some other examples I want to show you here and there. Heat affected, welded, fusion zone, welded zone or fusion, melted. So nearer to that, we have a heat affected zones are there. See some macro images we have done on this location. It is what it is. Here it is a double V. Here we have taken one V and we have welded. And similarly, it is a large thickness. Therefore, it is not possible to weld. Therefore, we have went for the double side welding also. Two V's we have taken and we have done the welding. See, we can able to understand these points. Double V we have taken and welded. So similarly, other zones we have taken the microstructures. The remaining part we will see you in the next session.